Hello everyone, we will be covering some problems on algebra today from the harder end of the AMC 12 and introductory AIME level problems. The first problem states, let f of x be equal to the absolute value of x minus p plus absolute value of x minus 15 plus absolute value of x minus p minus 15. 0 is less than p is less than 15, and we want to determine the minimum value taken by f of x for x in the interval x is greater than or equal to p is less than or equal to 15. So the key idea here is to simplify this expression for f of x by removing all of these absolute values. And so the way we can do that is, first of all, note that because x is greater than or equal to p, this means x minus p is greater than or equal to 0, so the absolute value of x minus p is just equal to x minus p. Then we note that x is less than or equal to 15, which means that x minus 15 is less than or equal to 0, so the absolute value of x minus 15 is equal to 15 minus x. And then we see that because p is strictly between 0 and 15, and x is between p and 15 inclusive, x minus p minus 15, the absolute value of that should be equal to the opposite of this, and this should be strictly less than 0. So we get 15 minus x plus p. Then we can write our expression for f of x as x minus p plus 15 minus x plus 15 minus x plus p, which gives us 15 minus p plus 15 minus x plus p, and these cancel, and you get 30 minus x. And we want to find the minimum value of f of x for x in this interval. And so the minimum value is obtained when x is the largest possible, which is 15. So 30 minus 15 is 15. So 15 is our final answer for the first question. The next question, we have this expansion, and by the binomial theorem, you get this, and you can write this as a sum of AKs, where each AK can be expressed in this general form for k ranging from 0 to 1000, and we want to find for which k AK is largest. So note that basically we want to find the first value of k such that AK should be greater than AK plus 1. So that all values after AK are less than AK. And so we're essentially finding the smallest possible value of k such that 1/5 to the power of k times 1000, choose k, is greater than 1/5 to the k plus 1 times 1000, choose k plus 1. And we can divide by 1/5 to the k, and this would give us 1000, choose k, is greater than 1/5 times 1000, choose k plus 1. And so then from there, we can apply some basic algebra, essentially. So we can use the definition of choosing, and we can write this as k factorial. We can write it like this, and that's greater than 1/5 times 1000 factorial, or k plus 1 factorial, and this becomes 1000 minus k plus 1 factorial. And we can divide by 1000 factorial on both sides, and we can also multiply by k factorial on both sides. And also we can multiply by 1000 minus k minus 1 factorial on both sides, which is just equal to 999 minus k factorial. So multiplying by that on both sides should just give you 1000 minus k here. So you would end up getting 1 over 1000 minus k is greater than 1/5 times 1 over k plus 1. And so then you can cross multiply essentially. So you should get 1000 minus k is less than 5k plus 5. So that would tell you that k should be greater than 165.8, which means the minimum value of k is 166. This means that a of 166 would be greater than a of 167, which would be greater than a of 168, and so on. However, all values of k less than 166, they are a of k is less than a of k plus 1, which means that this is greater than a of 165, which is greater than a of 164, and so on. Meaning a of 166 is the largest value of a of k. So the k value that we want here is 166. Okay, on to the next question. We want to find the least possible value of this product. And so the way we can do this is we can do a very clever grouping. We can group these two terms, and we can group these two terms. And so what we get when we do that is x plus 1 times x plus 4 is x squared plus 5x plus 4. And x plus 2 times x plus 3 is x squared plus 5x plus 6. And then you add 2019, and we notice that the difference between these two factors is 2. So we can actually write this as x squared plus 5x plus 5 minus 1 times x squared plus 5x plus 5 plus 1 plus 2019. And like, to make special emphasis, we can put this in parentheses. So we see that this is actually like a minus b times a plus b. Like, this is basically just a difference of squares. So if we expand it, so then we get x squared plus 5x plus 5 squared minus 1 plus 2019, which is x squared plus 5x plus 5 squared plus 2018. And we notice by the trivial inequality, this thing has to always be greater than or equal to 0, which means that the minimum value of this expression, which is equivalent to the original expression, should just be 2018. So rather, the minimum value of this is equal to 2018, which is our final answer. The next question is saying that we have positive integers a, b, c, and d that satisfy a is greater than b, is greater than c, and is greater than d. And then we have that a plus b plus c plus d is equal to 2010, a squared minus b squared plus c squared minus c squared is equal to 2010. And we want to find the number of possible values of a. So the way we can do this is, obviously the first instinct would be to apply difference of squares here. So we can write it as a plus b times a minus b plus d times c minus d is equal to 2010. We note that these a, b, c, and d are all positive integers. A is greater than b, is greater than c, is greater than d. So because they're all positive integers and they're like strictly greater than each other, the minimum difference between a and b is 1. The minimum difference between b and c is 1, and the minimum difference between c and d is 1, because they're strictly greater than each other and all positive integers. So in like the case in which they're as close to each other as possible, they're consecutive integers. So this means that basically a minus b is at least 1, so it's greater than or equal to 1, and c minus d is at least 1, so it's greater than or equal to 1, which means that a plus b times a minus b plus c plus d times c minus d is at least a plus b plus c plus d, which is equal to 2010 as well, which means we want the equality case. So we want a minus b to be equal to 1, and we want c minus d to be equal to 1, which would mean that b is equal to a minus 1 and d is equal to c minus 1. And if we substitute these two into this equation right here, then we would get the a plus a minus 1 plus c minus 1 is equal to 2010, which gives us that 2a plus 2c minus 2 is equal to 2010, which means that 2 times a plus c is equal to 2012, which means that a plus c is equal to 1006. And so from here we can easily see that the maximum value of a has to be 1004. The reason why 1005 does not work, and obviously 1006 does not work, because that would force c to be 0, but these are all positive integers. 1005 does not work because that would mean that c is 1. And then if c is 1, d is equal to c minus 1, so that would mean that d is 0. And again, all of these a, b, c, and d are positive integers. So that means the maximum value of a is 1004. Then, obviously, because a is greater than b and b is greater than c, a is greater than c. That means that if we divide 1006 by 2, we get 503. So the minimum value of a, such that a is still greater than c, is 504. And we see indeed that if a is 504, that means that b would be equal to 503, and then c would be equal to 502, and then d would be equal to 502 minus 1, which is 501. So this indeed works. So the maximum value of a is 1004, and the minimum value of a is 504. So if you want to find the number of possible values, all values of a in between these two numbers works. So then we would get 1004 minus 504 plus 1, which would give you 500 plus 1, or 501. So the next question is a logarithms question, and it states that a, b, and c are positive real numbers. We have these three equations, and then we want to find this. So this question, all you have to do is note that a to the power of log base 37 to the power of log base 37 is the same as this. And then we can similarly write the rest of the addends. So the second addend can be written like this, and then the third one can be written like this. So then we realize that this value is given to us, this value and this value are all given to us. So it becomes 27 to the power of log base 37 plus 49 to the power of log base 711 plus root 11 to the power of log base 1125. And then we can say that this is 3 to the power of log 27 is 3 to the power of 3. So you can write this as 3 to the power of 3 times 3 to the power of 3 to the power of log base 37 plus 7 squared to the power of log base 711 plus root 11 is 11 to the 1/2. So 11 to the 1/2 to the power of log base 1125. And this becomes, we can swap these essentially. And the same goes for this. And the same goes for this. And the reason being that that would give us something like a to the power of log base a something else, like b. And then that would just be equal to b. So we can write this as 3 to the power of log base 37 cubed plus 7 to the power of log base 711 squared. And then plus 11 to the power of log base 1125 to the power of 1/2. And this should give us 7 cubed plus 11 squared plus 25 to the 1/2, which is the square root of 25. And this should give us 49 times 7 is 343, and this is 121, and this is 5. And so that would give us 469. Okay, and then the next question is suppose x is in the interval of 0 to pi over 2 inclusive, and then we want to find 24 cotangent squared x given this. So as is common for logarithm problems, we can convert this into like an exponential equation. And so if we do that, then we would get the square root of 24 cubed sine cubed x is equal to 24 cosine x. And then what we can do is we can square both sides of this equation to get 24 cubed sine cubed x is equal to 24 squared cosine squared x. and then we can divide by 24 squared on both sides. We get 24 sine cubed x is equal to cosine squared x. And then we can rewrite cosine squared x as 1 minus sine squared x by the Pythagorean identity. So this we can replace with 1 minus sine squared x, and that would give us 24 sine cubed x. If we take these to the other side, plus sine squared x minus 1 is equal to 0. And this essentially gives us a cubic in terms of sine x. And so what we can do then is apply the rational root theorem. So we can try some values. So if we try -1, we get 24 times -1 cubed plus 1 minus 1 is equal to 0, and that gives us -24. If we try 1, that gives us 24 times 1 cubed plus 1 squared minus 1 is equal to 0, which gives us this left-hand side gives us 24. Here, this left-hand side gives us -24. Both these are not equal to 0. So, 1 and -1 are not roots. They're not equal. And then we can try 1/3 and -1/3. Again, all the possible rational roots are of the form P over Q, where P is a divisor of -1 and Q is a divisor of 24. So if we try 1/3, then we get 24 times 1 over 27 plus 1 over 9 minus 1. And that is equal to 24 over 27 plus 3 over 27 minus 1, which is indeed equal to 0. So we see that actually 1/3 is a root of this equation. So sine x is equal to 1/3 is a root of this equation in terms of sine x. And so because sine x is equal to 1/3, then that means that sine squared x is equal to 1/9. Note that we want cotangent squared x, which is cosine squared x over sine squared x, which is why I just found sine squared x. And then what I can do is 1 minus sine squared x is cosine squared x. And that value is 1 minus 1/9, which is 8/9. So we get 8/9 over 1/9 for sine squared x. Except this is 24 times cotangent squared x. So we can multiply this by 24, and we should get 24 times 8, which is 192 as our final answer. Okay, and for the next question, which is also a logarithms question, we can see that we have this sum essentially, and it goes from k is equal to 1 to 1,000, and we have a ceiling minus a floor of the same value inside, which means that really this can only be 1 or 0. And it basically, if the thing inside is an integer, then it's 0. If it's not an integer, then it's going to be 1. So that's all we really need to know. So then what we can do is just find when it's 1 or when it's 0. If it's 0, then we don't add this to the sum. We don't append it to the sum essentially or whatnot. So if we created some sort of counter, and then we would add k to that counter only if this expression is equal to 1. If this expression is equal to 0, then we don't add k to that counter. So then we just need to find when this expression is equal to 0, right? And those are the instances when we can basically subtract k from the sum of all the numbers, natural numbers from 1 to 1,000. And so those are values we would subtract from this sum from 1 to 1,000 because those are values we're not actually including. So it's kind of like complementary counting, except like not exactly. And so we can rewrite this log base root 2 to the k as log k over log root 2, and that becomes log k over log 2 over 2, which is 2 log k over log 2. And we notice that in order for the log 2 to cancel out, k should be a power of 2. Because if it is, then we get log 2 to the a over log 2 times that. And this can be written as 2 times a times log 2 over log 2. The logs 2's cancel out, and obviously a is like some natural number, and so then this becomes 2a. So we want k to be some power of 2. And the thing is, k ranges from 1 to 1,000. So there's only a finite number of powers of 2 that k can actually be. So k can go from 2 to the 0, 2 to the 1, 2 to the 2, so on, till 2 to the 9, which is equal to 512. 2 to the 10 is equal to 1,024, which is too large because it's greater than 1,000. And so we can sum all the numbers from 1 to 1,000. And then we can subtract these powers of 2 to get our intended sum. And of course, we want to find this mod 1,000, like the remainder when it's divided by 1,000, which is mod 1,000. So, we can calculate this. We want to find a mod 1,000, so you might as well directly do that. Mod 1,000. And so then this becomes 500 times 1,001. And then this is just a geometric series whose value is 2 to the 10 minus 1 by the geometric series formula. And you want to find this mod 1,000. We note that 1,001 is just congruent to 1 mod 1,000. So this becomes 500 minus 1,024 minus 1 mod 1,000. And then finally, this becomes 500. This is 1,023, which is just 23 mod 1,000. Which ultimately becomes 477 mod 1,000. And that is our final answer for this problem. Okay, and the next question, we have the series, and A is the set of positive integers that have no prime factors other than 2, 3, or 5. We have this infinite sum, and we want to find the reciprocals, the sum of the reciprocals of the elements of A, which can be expressed like this. And we want to find the value of that and then express as m over n, where m and n are relative prime positive integers, and find m plus n. And so the way we can do this is we can notice that each of these fractions are of the form 1 over 2 to the a times 3 to the b times 5 to the c, essentially. And so essentially we have this infinite sum of 1 over 2 to the a of fractions of this form. And a, b, and c are non-negative integers. And they span all the terms of the infinite sum. And so the infinite sum can be written as, from this kind of summation where we have each of these variables ranging from 0 to infinity. And then we have all the possible combinations of a, b, and c's, and 1 over 2 to the a times 3 to b times 5 to the c. And we have all possible combinations of a, b, and c where a, b, and c are non-negative integers. So we can have like infinitely many combinations of a, b, and c, and then it's a sum of all such fractions, essentially. But then what you realize is that if we're able to choose any value of a, any value of b, and any value of c, we can just essentially write this as a summation from where a goes from 0 to infinity of 1 over 2 to the a times the summation from b is equal to 0 to infinity of 1 over 3 to the b times the summation where c goes to 0 to infinity of 1 over 5 to the c. And then this just basically becomes a product of 3 different geometric series. So using the infinite geometric series formula, we get 1 over 1 minus 1/2 times 1 over 1 minus 1/3 times 1 over 1 minus 1/5. And this should give you 1 over 1/2 times 1 over 2/3 times 1 over 4/5, which would give you 2 times 3 halves times 5/4. And that gives you a final answer of 15/4. And these are relatively prime. The numerator and denominator are relatively prime, so your final answer is 15 plus 4, or 19. That's this problem. For the next problem, this is basically an arithmetico-geometric series that says this is equal to this, which is an arithmetico-geometric series essentially, and you want to find essentially the value of z, and then it'll be of this form, and you want to find this. And so the way you can do this is you can actually just multiply both sides of the original equation they give you by z. And so when you do that, you get iz cubed is equal to, and this is a standard way of handling with arithmetico-geometric series. And so what you get when you do this is z plus 2 plus 3 over z plus 4 over z squared plus 5 over z cubed, and so on. And then your original equation is this. So actually we can subtract these two equations, and if we do that, then on the left hand side we get iz squared times z minus 1, and then we notice that we can group the subtraction like this, and so on. And what that would give us is z plus 1 over z plus 1 over z squared plus 1 over z cubed. And as you can see, this goes on, and this is just an infinite geometric series on the right hand side. And so then we can further simplify this equation. The initial term is z. The common ratio is 1 over z. Multiplying the numerator and denominator by z. We can better write this fraction essentially to become z squared over z minus 1. So then we get that iz squared times z minus 1 squared is equal to z squared. And this tells us that z minus 1 squared should be equal to 1 over I. And 1 over I is just negative I. So z minus 1 is equal to plus or minus the square root of negative I. And this means that z is equal to 1 plus or minus the square root of negative I. And so thus, we actually got the value of z in this form. And that means that n is equal to 1. And so the floor of 100 times 1 is equal to 100. And that's our final answer. And the next question says that a, n, and b sub n are sequences of real numbers such that 2 plus I to the n is equal to an plus bni for all integers n greater than or equal to 0, where I is equal to the square root of negative 1. And you want to find this infinite sum from n is equal to 0 to infinity of an bn over 7 to the n. So we can approach this essentially by first squaring the first equation they give us. Because note that we want to find something in terms, or that has some term kind of like a sub n times b sub n. And if we square the first equation they give us, then we will get something like this. In fact, it would be 2 times a sub n times b sub n times I. So if we do that, then we would get 2 plus I to the n squared plus 8 is equal to an plus bni squared. And then that would, we can swap these two exponents and get 2 plus I squared to the n is equal to an squared plus negative bn squared plus 2an bni. And then, so this is equal to 3 plus 4i to the power of n is equal to a sub n squared minus b sub n squared plus 2an bni. And so then we see that the imaginary part of this left-hand side should be equal to 2 times a sub n times b sub n. And so that means that a sub n times b sub n should be equal to half times the imaginary part of 3 plus 4i to the power of n. And so we can utilize this. Because this is true, we can say that the original expression becomes a sub n, b sub n over 7 to the power of n should be equal to half times the imaginary part, writing it here for more space, half times the imaginary part of the summation, n is greater than or equal to 0, of 3 plus 4i to the power of n over 7 to the power of n, which is equal to half times the imaginary part, and this just is your matrix series. And the common ratio is 3 plus 4i over 7, and the initial term, since n starts at 0, is just 1. This is 1 over 1 minus 3 plus 4i over 7. And we want to find the imaginary part of this and multiply by 1/2. So we see that 1 over 1 minus 3 plus 4i over 7, we can multiply the numerator and denominator both by 7 and get 7 over 7 minus 3 minus 4i, which is equal to 7 over 4 minus 4i. And so this is equal to 7/4 times 1 over 1 minus i. Multiplying the numerator and denominator of this by 1 plus I, we get 7/4 times 1 plus I over 2, which is equal to 7/8 times 1 plus I. And so ultimately, we get 7/16 times 1 plus I. And the imaginary part of this is what we want to find. And the reason why we get 17 times 1 plus I is because 7 over 16 times 1 plus I is because this is 1/2. So we want to find the imaginary part of this, and that would just be 7 over 16 times the imaginary part of 1 plus I, which is just 7 over 16 times 1. And that gives us final answer of 7 over 16. Okay, moving on to the next question. The next question states that we have a sequence of numbers defined recursively by a1 is equal to 1, a2 is equal to 3/7, and we have this recursion for all n is greater than or equal to 3, and we want to find a sub 2019. So we can note that actually if we divide the numerator and denominator both by an minus 2 times an minus 1, we get something very interesting, which is that an is equal to 1 over 2 over an minus 1 minus 1 over an minus 2. And then we can take the reciprocal of both sides of the equation to get 1 over a sub n is equal to 2 over a sub n minus 1 minus 1 over a sub n minus 2. So then we can see that we can write this as 1 over a sub n plus 1 over a sub n minus 2 is equal to 2 over a sub n minus 1. And then that gives us that 1 over a sub n plus 1 over a sub n minus 2 over 2 is equal to 1 over a sub n minus 1. So we can basically just define a new sequence of the reciprocals of a sub n. So b sub n is equal to 1 over a sub n. And that would mean that b sub n plus b sub n minus 2 over 2 is equal to b sub n minus 1, which means that actually, like, this is sufficient to show that the sequence b sub n is an arithmetic sequence. Because if we take the arithmetic mean of the two terms that are adjacent to another term, then it should give that term. So if we have a comma b comma c, and these are like adjacent terms in arithmetic sequence, then a plus c over d should be equal to b, and that's what we see here. So that means that b sub n is an arithmetic sequence. We see that b sub 1 is equal to 1, and b sub 2 is equal to 7/3, which means that the common difference d for the sequence b sub n should be 4/3. So that means that b sub 2019 should be equal to b sub 1 plus 2018 times the common difference d, which is just 1 plus 2018 times 4/3, which should be equal to 1 plus 8,072 over 3, which gives us 8,075 over 3. And that means that A sub 2019 is 1 over B sub 2019, which is 3 over 8,075. And so P plus Q would be 8,078. And we're done with this question. And the last question that we covered in class is this algebraic manipulations and systems of equation question. Is just mainly a systems of equation question, but there are some clever insights that we can use in this question. So we have the x and y are real numbers, x is greater than y, and we have these two equations. And we want to find the value of x. So the first thing that we can do is we can say that the first equation actually can be rewritten in a very nice way. So we can write the first equation as x squared y squared plus x plus y whole squared equal to 40. And the second equation is xy plus x plus y is equal to 8. If we square the second equation, then we should get x squared y squared plus x plus y whole squared plus 2xy times x plus y is equal to 8 squared, which is 64. And if we subtract these two equations, then we should get that 2xy times x plus y is equal to 64 minus 40. And dividing by 2 on both sides, and this is 24. So dividing by 2 on both sides, you get xy times x plus y is equal to 24. So is equal to 24 over 2, which is 12. So then from what we can do, from here what we can do is that we can let x, y, and x plus y be roots of some quadratic equation. And we have that the product of xy and x plus y is 12. And we have that the sum of xy and x plus y is 8. So then if the sum is 12 and the product is 8, then we can write our quadratic equation as a squared minus 8a plus 12 is equal to 0. Then it follows that using the quadratic, or rather, we can just factor this to find the roots more easily, and we should get a minus 2, a minus 6 times a minus 6 is equal to 0. So then a is equal to 2 and 6, which means that in some order, xy and x plus y is equal to 2 and 6 in some order. And so then if x plus y is equal to 2 and xy is equal to 6, then we can say x and y are the two roots of another quadratic equation, and the sum is 2 and the product is 6. So then we can write a quadratic equation for this, which is b squared minus 2b plus 6 is equal to 0, and then x and y would be the roots of this equation. But the discriminant of this is negative 2 squared minus 4 times 1 times 6, which is 4 minus 24, which is less than 0. So there are no real roots to this, and we know that x and y are real numbers, which means we need to try the other possibility where x plus y is 6 and x times y is 2. So if we try that, and we can erase this because it did not work, then what we get, so we're trying the case where x plus y is 6 and xy times y is 2. And so then x and y would be the roots of the quadratic b squared minus 6b plus 2 is equal to 0. And here, in fact, if we take the discriminant, we'll see that it's greater than 0. So if we find the roots of this using the quadratic formula, we get negative 6 plus or minus the square root of negative 6 squared minus 4 times 1 times 2 over 2, which is 6 plus or minus the square root of 36 minus 8 over 2, which is 3 plus or minus, this is the square root of 28, which is 2 root 7, so plus, and we're dividing by 2, so plus or minus the square root of 7. So the two roots of this quadratic equation are 3 plus square root of 7 and 3 minus the square root of 7. However, in the question, it tells us that x is greater than y. So x should be the larger of the two roots, and so thus x is equal to 3 plus the square root of 7. That is our value of x. And that is the last question that we did in the class. And the rest of the questions were assigned for homework.